So Christian Hulteberg is a professor at the Department of Chemical Engineering here at Lund University. He also has a master degree in business administration, and his research is on the transition from fossil to renewable feedstocks in the chemical and petrochemical industries. So looking into new process pathways for using renewable feedstocks, aiming to reduce them into existing material streams, where his focal point is heterogeneous catalysis, but he also looks into non-catalytic processes and gas cleaning methods. This also includes the assessment of the economic performance as well as regulatory instruments. Next to that, he has a background as a serial entrepreneur, starting up a number of companies, and he also serves as an expert to the European Commission, to the Research Council of Norway, and to the International Energy Agency. And with that, Christian, the floor is yours.
Thank you. That's a very nice introduction. I appreciate being here talking about carbon dioxide and also the opinion or option to do direct air capture, which is something that I haven't looked into in too much detail before, but I will be doing my best to convey that findings I did on that today. So the carbon dioxide is, of course, a complex molecule. It's complex in its simplicity. So you have a carbon and two oxygen. The molecule is at the end point of any energy conversion aspect. So it has the lowest energy available in the spectra. And we now want to use it as a starting point for doing things. And why do we want to do this when there are other nicer energetic options available? Well, first of all, when we move to a more electricity-based society, we need a source of carbon atoms because it's not just energy. Energy is a very important and central part, and the discussion on energy carriers and all that is very relevant, but we also need materials and we need chemicals, and they are used in many different applications where we see a good use for them. They contribute to lowering material weights, functional materials, polymers, and you know this almost as good as I do, at least, that chemicals will contribute significantly to any society. But when we move away from fossil-based transportational fuels, in this case, crude oil or refined crude oil, there will be a lack of carbon also in the chemical industry, because the chemical industry is using about 5, 6, 7% of the world crude oil. It creates much more of the value, but that means that with that small share of each barrel of oil, the chemical industry will not be able to sustain this on their own. So if there is a drastic reduction in the use of fossil oil in transportation and heating, the chemical industry will not be able to fund the prospecting and extraction of crude oil on its own. So there is a need to switch over to something different. And well, carbon dioxide is a quite attractive option, especially given its availability. So global emissions, about 24 billion tons per annum, gives us a very good starting point. The CO2 needs to come from somewhere. And right now, the best option from an energy perspective is to use point sources like chemical plants, combustion plants, and other sources where you have CO2 emissions in rather high concentrations. They are perhaps not 100% pure, but they start in the teens and move up to 30, 40% in gas streams. We still need to spend some energy in when we capture the CO2, and we need to spend energy in releasing the CO2. And then we need to, of course, recover the sorbent to get back to the point of where we are. I mean, the recovery is done during the release. So we need to invest some energy to concentrate the CO2 before we can actually do reactions with it or anything with it, to be honest. So there is a cost of this concentration energy going in. And there is a lot of studies looking at this, and you can see that when you look at point sources, and point sources are the ones that I mentioned before, it's flue gases from combustion plants or fossil energy plants or bioenergy plants. It's also chemical plants where you can find higher energy level or higher concentration levels. And then the other option would be the direct air capture, DAC. The point sources, they usually end up somewhere between 5 and 8 kilojoules per mole of CO2, and the direct air capture somewhere between 20, 22 kilojoules per mole. So it's significantly more energetically favorable to use the point sources, which is also why the cost goes down. But it's not that huge of a difference, so it's not proportional to the concentration. I mean, if we look at 40% and we end up with 5 kilojoules per mole, and we then compare that to 22 kilojoules per mole for 400 ppm, which is the concentration in air. The energy input that we need to provide is usually thermal. So in most applications, we have energy coming in to the system in the form of heat, either steam or high temperature water. Medium temperatures, that's the most common feature, somewhere between 120 and 140 degrees C. So it's not high quality steam, but it's still rather high heat flux that is needed. There are some processes, especially the ones that use precipitating systems, that can use lower energy, lower quality energy. And when you do this regeneration, you can also combine it with pressure swings so that you can change pressure and reduce the temperature needed. A very interesting field that I see is when you can use electricity directly. So instead of, like we discussed in previous talks, using CO2 and hydrogen to produce something where the hydrogen is derived from electricity, we can actually use electricity and do in situ reactions directly on the capturing media. So that's very interesting to me. I just did a split screen of the most common methods here. So if you take from left to right, we have the method of separation for a few of them. Then if the second column would be the suitability for direct air capture, and then some thoughts or comments just to qualify these different methods. And first of all, the aqueous amine type capture. That's the most common type that is used, where you take a chemical compound called amine, which contains a nitrogen group. You mix it with water and you have it contact the flue gas, or the, well, not the flue gas, but the industrial gas, and flue gas as well, but not for direct air capture. This is what is used in large scale industry. This is the largest thing that you can find currently implemented. So it's really something that is very commercial. We also find solid amines, so the second row, which are the same type of materials, but they are now supported on other types of solid materials, which means that you get away from the use of solvents. You need lower energy input because you don't have to heat the water solvent. It's unfortunately sensitive to water and other impurities. And in this case, we see amines supported on silicates, carbon, and other solid materials. And it's technology that is on the rise. So it's something that is being developed, but it's in, I would say, TRL 6.7, where it's commercially demonstrated, but not fully commercialized. Potassium carbonate is another well-established working mechanism type scrubbing, where you use an alkaline salt in water solution with contacting the media that you want to remove the CO2 from, and it's very resistant to oxygen. So if you compare aqueous amines and potassium carbonate, the throughput would be lower for the potassium carbonate, lower reaction rates, higher flows of the potassium carbonate, but you will have less oxygen interference. So maybe better suited for the use in flue gas treatment. And the final method that is discussed is chilled ammonia, where you're using ammonia at low temperatures, and yeah, it's not suitable for direct air capture, I would say, due to the loss of ammonia. And basically, just putting out there quite bluntly, the higher the concentration of the CO2, the lower the cost of concentration is, because the energy input decreases because you can do it more efficiently. You can also do it with a more mature capture technology. And of course, the lowest concentrations are for direct air capture. And when you look at direct air capture, it's much more limited with respect to diffusion. There's much lower transport rates inside the equipment because the concentrations are so low. So you need much more time to allow for movement of CO2 in the system. And that also means the low concentration that you need much higher volumes to be processed. So if you have high concentrations, you can do with much less gas. But if you have low concentrations, the equipment sizes grow large quite rapidly. Pressure drop becomes a large part of operating expenses and very large process units. And you've seen these pictures, I assume, where you have huge concentrator farms look outside in the Badlands somewhere, and they supposed to capture all the CO2 by using forced air fans pushing it through some kind of capture medium. But this is, of course, a simplified picture because it also builds a lot of inlet-outlet tubings and all that. So when you take it and turn it into a reality, it becomes something different and much more complex. Another thing that you might not think of is how you use the land in between, because you can't expect to use the same air with a lot of these systems, so that you can use about, well, you have to consider the land use in between and what to do with those as well. And water might also be something that is consumed, especially for those technologies where you use steam for regenerating the adsorbent. But it's still significantly more efficient way of capturing CO2 compared to growing forests. So yeah, if that is your measure, then you're still better off. CO2, it's normally derived from fossil fuels in energy production or in chemical industry, but also from biological transformation processes like ethanol fermentation production. And yeah, there's not much direct air capture done today. We do use carbon dioxide today in the chemical and in other industries, either purely physical utilization where you use the molecule as it is. It could include the change in aggregation state, so you use CO2 ice, for instance, for cooling. And we also use CO2 as a chemical starting point today, where we crack the molecule or convert it into some other product. And either direct use or a booster can be envisioned. Physical utilization, dry ice. We also like our fizzy drinks, like soda pop or beer and other carbonated drinks. But it's also a refrigerant. We use it as a welding medium, and it's also used as a solvent in chemical processes. We use it in physical utilizations for boosting, so enhanced oil recovery. The original use of CO2 storage in natural gas and oil fields was, of course, not for removing the CO2, but to enhance the production of oil and natural gas. It can also be used in power production via supercritical cycles. In the chemical industry, we use it for making carbonates, we use it for making urea, salicylic acid, formic acid, and some other carbonates, like propylene carbonates. So there is a use today in the industry for carbon dioxide. And well, you can also envision doing it in a more elaborate way, where we add it in smaller amounts, especially for methanol synthesis. It's very common that you add CO2 to your natural gas in ordinary existing production plants, a few percentage points, to get a better relationship between carbon monoxide and hydrogen in the process. And yeah, you can also envision doing dimethyl carbonates, dimethyl ethers, and polyurethanes. And yeah, algae is always up there as well as utilizing the CO2. When we look at electrification, the electrification of the chemical industry to me is something that's going to change how we look at chemicals forever. We're opening up to direct electrochemical conversion of the carbon dioxides, like formic acid, formaldehyde, using electricity basically to lift it back up in energy. But there's also the routes that we have been talking about before, like producing hydrogen through electricity and then going backwards, using the hydrogen to remove oxygen from the CO2, producing CO and hydrogen. And that's, of course, referred to as synthesis gas. And from synthesis gas, you can actually go basically anywhere in this flow chart here that you like. So you can do synthesis gas, you can go to methanol. You can, of course, do the Fischer-Tropsch route, go to diesel fuels or olefins. The olefins can be used for making chemicals or fuels. And yeah, pure hydrogen is possible. You can do alcohols and substitute synthetic natural gas. Those are also options in this product tree here. As long as, or as soon as you get to CO and hydrogen, things sort of solve itself, and you can utilize a lot of the existing chemical and petrochemical industry infrastructure already. Yes, and finally, just with conclusions, concentration is everything. We need a concentrated starting point, especially if we want efficient conversion. We can't use very large volumes, so using CO2 in air it's a prerequisite that we do concentrate it. The concentration costs energy, and that's higher energy cost per molecule depending on the concentration. So lower concentration, more energy cost. The current use of CO2 in the chemical and petrochemical industry is actually quite large. So that's a little surprising, but I think there's a future use in making fuels and chemicals if you can find a nice way to integrate renewable energy production with the CO2 capture. And yeah, direct air capture still has potential, and there are some demo plants, but it's far from large-scale realization. And with that, I'd like to thank you for your attention and yeah, leave it back to the moderator.
Great. Thank you, Christian. Given time, I think we will just take one question and keep the others until the Q&A session. And the question is on CO2 capture from seawater. Do you have any idea on the energy costs associated with that?
No, I'm sorry, I don't. So that was a very short answer.
Then maybe we can take one more question. A question on whether you can elaborate a bit more on why technical direct air capture is considered better, it says between quotes here, than collecting the carbon via the biomass route. So why would you go for DAC instead of getting the carbon from a biosource?
Well, it has this is my personal opinion, of course, but it has to do with the higher efficiency compared to forests. So you can, in the same land space, collect more CO2 than if you grow forests. You don't have to worry about biodiversity and those kind of things. You can do this on badlands or deserts or things like that, where you don't necessarily have the option of growing things. And I did mention water consumption, but water consumption will be significantly lower also compared to growing biomass. So there are a few advantages there.
Yeah. Thank you very much again, Christian, and we'll get back to you during the main Q&A.